Here we are again. So this video is on the nuts and bolts of the ozone layer. And so to start, with respect to the ozone layer, the thickness of the ozone layer is measured in Dobson units, DUs. So the way in which they approach this Dobson unit is if you took the entire ozone layer and squeezed it down such that the pressure of ozone would be 1 atm, then 1 du, 1 Dobson unit, is a thickness of 0.01 millimeters. So to put that in perspective, the reason they do this is to get a nice round number that you can relate. And so if, say, you're at a temperate region, this should say temperate. You're in a temperate region, the ozone layer is about 350 DUs, or 3.5 millimeters. I believe on the equator, it's more like 250, and at the poles, in a healthy condition, it's at about 450. So what we have are different types of radiation coming from the sun. We have our IR, this is our thermal radiation. We have our visible, and we have our ultraviolet. So we've already have kind of delved into what these types of radiations are doing to the gaseous molecules. We know that IR causes the atoms, the bonds, to vibrate in these molecules. In visible, what we get is when this light interacts with the molecule, there becomes electron excitation. We get absorption of that energy and then relaxation back down to what we call the ground state. In ultraviolet, we get the same, but it's a very strong electronic excitation. And in some cases, you can actually get a breaking of a bond, or ionization, or the production of an excited state. So ultraviolet is similar to visible, but depending upon how high of energy the ultraviolet is, you can again form free radicals and ions. And so with respect to ultraviolet, this is going to be the focus of this talk. It's the ozone that prevents much of this ultraviolet from coming into the atmosphere. And so what we can do is we can break down UV into UVA, B, and C. UVC is very high energy, low wavelength, and then towards UVA, this is approaching visible. So 400 is violet, so we are now up against and just slightly higher energy than the visible region. And so you see these type of notes on, say, sunscreen bottles and such, in terms of what the sunscreen might protect. And so what we see here is that these higher wavelengths are absorbed by either ozone, or in terms of the very intense UVC, they're actually absorbed by oxygen and nitrogen. But this ozone layer that we have at the top of the stratosphere is very important in absorbing the UVB range, and it does still let some through. And this is again why we wear sunscreen. So, but if we didn't have the ozone layer, then what would occur is that we would see more of this UVB penetrating through the atmosphere and getting to the surface of the Earth. And so what we'll cover here is the natural formation and destruction of this stratospheric ozone layer. So what we could say that before human activity, this ozone layer was at a steady state. And so it forms and decomposes at kind of a constant rate during daylight hours. And so what we have in terms of generation of ozone up in the stratosphere is the reaction of oxygen atoms and oxygen gas to form the ozone and create the heat. You guys remember the temperature profile of the atmosphere. And so this reaction occurs where we get this nice sweet spot of oxygen concentration and still enough UVC to cause this reaction to occur. And so destruction occurs the same way, where again, we're in an environment where we still have a lot of UV. And so the ozone reacts with the UV light to form oxygen and an oxygen atom. These are in an excited state. This is how an excited state is noted with a star. And this just means that the electrons within the molecule or atom are at a energy that's not in the ground state, not at the lowest energy state. And so this figure here kind of just shows this constant balance of creating and destroying the ozone. And during this process of creating and destroying the ozone, UV is absorbed. And that is how the ozone layer works. So with human activity, there then became the process of catalytic destruction of ozone. And so, as I'll show in a couple slides, we have produced pollutants that have the ability to get into the stratosphere, have a very long lifetime, and can do this destruction of ozone that doesn't have a creation component to it. And so let's look at this generic sequence of reactions. We'll call it a mechanism. And let's just let the catalyst be X. So we remember what a catalyst is. Catalyst lowers activation energy. Remember, activation energy is that threshold in which a reaction needs to get over in order for the reactants to turn into products. So the catalyst lowers that threshold and makes the reaction go much faster. So we have our ozone, and the ozone reacts with the catalyst to form an intermediate. We're just going to say XO. So we generate oxygen gas, and then that intermediate goes on to react with oxygen atoms within the stratosphere to reform the catalyst. That's a part of the definition of the catalyst, is it does not get destroyed, and produce more oxygen gas. And again, this is occurring under conditions where the threshold to form the products is much lower. So this reaction goes much faster, and we get the destruction of the ozone molecule. I want to add, this is again all occurring under daylight hours. These are photochemical reactions. They do need sunlight. They do need ultraviolet light in order for the reaction to progress. And so what I have here at the bottom is just a plot showing the reaction taking place. And so if we have, say, ozone under natural conditions meaning uncatalyzed, that ozone will react with the UV light, and it needs to get over this threshold in order to make these products. And so up here at the very top of the activation energy, this is what we call the transition state. This is where the reaction occurs and where the reactants end up turning to products. It's also, in some cases, called the activated complex. These terms are synonymous. However, in the presence of a catalyst, we now have much lower activation energy, much lower, and we quickly can convert the reactants into products. Both of these reactions are endothermic, and so they're absorbing the energy from the ultraviolet. So in the next two slides, we're going to use CFC as an example of how a catalyst can be formed to destroy ozone molecules. And so CFCs, which are chlorofluorocarbons, are one of the primary culprits for the destruction of the ozone layer. And CFCs were actually invented by the same scientists who you saw as a character in the Cosmos video, Dr. Kehoe. Dr. Kehoe is the one who developed the lead additive, the tetraalkylated lead that was put into gasoline that polluted the earth. He also is the one who came up with chlorofluorocarbons to be used as refrigerants. So that is quite a record for one person to poison the entire earth with lead and also attempt to destroy the ozone layer. There are other compounds that we need to consider that humans have used as flame retardants, as pesticides, and they are brominated compounds. So nonetheless, let's see how a CFC produces a catalyst that destroys ozone. So let's look and see how CFCs, we could call it freon is another term, destroys ozone. So the first step is where the freon gets into the stratosphere and reacts with, say, ultraviolet radiation to form free radicals. Now, a free radical is an atom or molecule that has a lone electron. We know that electrons like to be paired. That's how they're stable. But a free radical is something with a single electron, and so free radicals are very reactive. So that is our catalyst. Our catalyst is the chlorine radical, and that will react with ozone to form an intermediate, another free radical. This is some sort of chlorine oxide free radical, and it generates oxygen. The intermediate, which is very reactive, reacts with oxygen atoms in the stratosphere to reform the catalyst, and we get more oxygen. So we get an overall reaction showing, again, the destruction of the ozone. So we have our intermediate, we have our catalyst. And just note that this catalyst, it can go on to destroy 100,000 ozone molecules because it keeps being regenerated. And we can come up with this value based upon the known residence time of a chlorine radical. And so at some point, that chlorine radical will react with some other molecule in the atmosphere and destroy itself. But nonetheless, we can see that these CFCs, brominated compounds, are very detrimental to ozone and have depleted ozone in our upper stratosphere. So our next video will look at that depletion and the formation of the ozone hole over Antarctica.